In this video, we use any Linux architecture with QEMU User to assemble and run for ARM64. We create a simple bash script. We write the header assuming QEMU is installed. We use arch-linux-gnu as to assemble the specified input file name. The O option defines the output using $10. Remember to use $1 for the argument. For linking, we use LD. We use $10 for the object file, then O and $1 for the executable. It runs with QEMU arch. We type ./1 to indicate the executable, then a semicolon, the echo command, and the $? Symbols. To remove the temporary files, we use the rm command with $10 for the object and $1 for the executable file. To solve example 10, we write the global directive, start label, data section, and two variables a and b with defaults. Then the text section and start label. We load the memory address of A into x1 and the address of B into register x2. Now, we load the content of A into x3 via its address using the exact same instruction for B, loading it into x3 too. With both values, we store the value of B into the address of A, load the least significant byte, and exit the program. We use the script IceLDEC with the name tens3 to execute, and it prints the expected value 255. To solve example 11, we write the full initial code. In x0, we place 1 for stout read artiroot, then load the message address. Into register x2, we place the required size of the message, 14 bytes. In x8, we place 64 for writing data. It is wise to leave the default 0 in register x0 as the return value to show everything went smoothly, then the exit. Below, we place the data section with the MSG variable. If placed below, it is not needed to specify text up above. When executed, we see the message and a 0. We edit the script to remove echo, and it only prints the message text. To solve example 12, I have the code ready to explain in detail. It is split into parts. Part 1 prints a prompt. The second part requests user input directly from the keyboard. The third part prints the message inside the buffer. The buffer has a size of 16 bytes allocated. The first line of each part is the code for output and input now. In part 1, we print enter a text. We use syscalls code 64 in register x8 to write the text to the screen. In the second part, we use code 0 for standard input, the keyboard. We use the buffer of 16 byte size. For screen output, we use code 64. And for keyboard input, we use code 63, as shown here. With similar structure, code 64 is in part 1 and 63 in part 2. Part 4 handles return and exit. We write the data section below to avoid writing text above. We execute as LD and it asks for input. We write a message longer than 16 bytes. This splits the text and triggers an error in the terminal later on. The buffer was filled, and the rest stays in the keyboard input, causing an error with enter. We run it again safely. Now it prints correctly. To change the requested message size, we must place a larger value for the input buffer size. To solve example 13, we declare a pointer variable to address the new memory address requested from the break. Part 1 invokes break. Part 2 associates the pointer. Part 3 requests memory, and Part 4 handles the logic. The fifth part loads the value, returns it, and exits. We use code 214, the invocation for break calls. It is advisable to have the list of codes from a website. We select ARM64 to see codes descriptions. Among them are open at and close for files, read and write, and exit. We scroll down to see more syscall numbers now. In the higher numbers we find code 214, the break command, plus a link to the man page for full details. There we find arguments and operating system operations. We return to the program and use x0 with the value of 0. This returns the last data address available. We load the pointer and store the address returned by the break call. To that address we add 4 bytes and execute break again. But now with the pointer to request that specific memory, then we can access that memory address and store the value 100 in it. The pointer addresses the new memory location. We load the value from the new address, return it, and exit. We run the program and it prints the value 100. To solve example 14, we create the program with nano and edit it. We write global and start labels properly. We use the immediate value 0 and place it in register x0 with mov. Then we add register x0 with immediate value 100. For this we use ADD. In high level it is like assigning 0 to x0 and then writing x0 equals x0 plus 100 naturally. Once the sum is done and left in x0 for return, we write the exit code with 93 in x8 and the svc0 call explicitly. Now we execute the program via the addlec script, so echo prints the return value, which is 100 as expected. To solve example 15, we declare in data a variable named a, type word, with negatives values 1, 2, and 3. We load the address of a into x0 with LDR, then load position 0 into x1 and x2 with an offset of 4 bytes total. Being the array at position 1, we load into x3 from x0 with an offset of 8. Being the array at position 2, we use ADD to add x1 and x2, leaving the result in x0. Then we add x0 and x3, leaving it in x0. We negate x0 with neg. Then we write the exit code and the sum was left in x0. We execute the script and get the value 6 as the result. This has been all for this video. If you liked it, subscribe. Please like and activate notifications. See you in next video.